Alright, this is my first video for Strength of Materials, EAS212 for PSU. This first example is just going to be kind of a statics review. We'll go over first to find the support reactions, and we'll do that by creating an FBD and then our equations of equilibrium. And then second, we'll make a cross section cut, FBD at point C, and determine the internal forces at that point. So going over the question though, the shaft is supported by a smooth thrust bearing at A and a smooth journal bearing at B. Determine the resultant internal loadings acting on the cross section at C, which is right there. So at A, going over our first step, which is the support reactions, at A, we'll have forces in the vertical direction and in the horizontal direction. We can already see that if we sum the forces in the x direction, we actually don't have anything except ax. So we can just see that ax will equal 0, and that will just immediately go away. So we'll only be looking at a sub y, and then b will also. So this is like a is like a pin, and b is like a roller. So then we have the distributed load going across this part with C halfway in the middle, and this 900 newtons down. Alright, so let's first do our FBD. It's pretty simple, so make sure to draw what your coordinate system you're using is. We can keep this pretty simple too. Go back to black quick. Just a simple beam. Want to draw our loadings. So their distributed load, 600 newtons per meter, and the resultant of that is going to be 1200 newtons. And then we have the 900 newtons over here at D going down. And then we're trying to solve for our support reactions at Y and our support reactions at B. And here is C, which is where we're going to do our cross section and find our internal loadings after we found these support reactions. In general, when you're drawing these FBDs for class, you'll want to include the geometry. So let's just go ahead and do that. Make sure we don't skip any important steps. So from here to here, we have 1 meter. From this point to C, another 1 meter. To the end of the distributed load, another meter. Here we have 1.5 meters, and another 1.5 meters. If you're doing this for homework, make sure to use straight lines. Pull out your ruler, whatever you need to make a straight line. But for this, we'll just quick and dirty. Alright, so we can sum the forces in Y, but that still leaves us with 2 unknowns, not really getting us anywhere off the bat. So let's sum the moments around point A, which will be equal to 0. Our first loading is AY, but that will not cause any moments at point A. Our next is that distributed load, and we're going to look at the resultant force, that 1200, and see which way what moment that causes at A, and it'll be pushing down, causing a negative moment going clockwise. So 1200 newtons times the distance of the resultant force, that 1200, from the point we're summing about, which is A. So that point right there. So that's 2 meters times 2 meters. And then we have our BY, just pushing upwards, so causing a positive moment at A. And we will add another meter, so 3 meters, 4.5 meters away. Sure to get our units on there. And then we have the 900, also causing 900 newtons, causing a negative moment, which is clockwise. And that's 6 meters away. Alright, so we'll sum all those up, and we get negative 7,800 Newton meters. But then we'll add it to the other side, get BY over here, divide both sides by this 4.5, get that BY is equal to 1,733 Newton. These meters will cancel out. Alright, now we can sum the vertical forces. So we get AY plus BY, which we now know is 1,733. And we could just combine our negative forces, so 1,200 plus 900. Bring that to the other side, or first actually subtract 2,100 from that 1,733, and then bring it to the other side, and then we'll get A sub Y, just 367 newtons. Like we said, AX is equal to 0 because we have no forces in that direction besides that support. Alright, so step 2, now that we know what these supports, what's happening at that support, is to make a section cut right here at C. And we can keep either side. It's kind of just whatever seems easiest to you. So you can draw it with the left side intact, or you can draw it with the right side intact. We're just going to keep the right side. So this will be our section. This will be the right side of our member. Draw the forces that we know, and we will have about half of that distributed load going across, which is 600 newtons per meter at C. Here's our BY. Here's that 900. This is at B, this is at D. And then let's look at what those internal, let's do that in green, what those internal forces, what do they call it, resultant internal loadings, what those are. So this will be our shear. We always want to draw them in the positive direction. So let me just apply this here. Here's our normal, and then we have our internal bending moment. Ugh, it's terrible. Alright, just to remind you, this is what the sign convention is for shear and normal. Let's do this in brown. For shear, we want it that when it's positive, it causes a clockwise rotation. For our moments, we have them both kind of being a couple moment. Just like that. That's our moments. This is our shear. And then normal, and this we'll see this sign convention. Normal is drawn, or axial forces, normal or axial forces are drawn positive when the member is in tension. So this will continue, tension, positive, compression, which would be going that way. Compressing the member would be considered negative. All right, let's get to finding these internal forces. All right, what do we want to do? It looks like the shear is probably our easiest to find. Let's make sure to add this geometry. So from here to here, we get 1 meter. Here to here, not really drawn to scales, 1.5. Here to here is another 1.5 meters. All right, sum those forces in the y direction. First off, on the left, we got V going up. We get minus, we calculated what this resultant of our distributed load. So what would be happening if we converted our distributed load to be a point load? We have 600 newtons acting a half a meter from our cross section from C. So that's going down, so negative 600. Let's give ourselves a little bit more room actually, or maybe not right as big. Sum of the force in y equal to 0. We got V, got minus 600, positive, don't forget our units, negative 600 newtons, positive 1,733 newtons, and another negative 900 newtons going down. Alright, so sum all those up. Minus 600 plus 1,733 minus 900, get 233, and we want to subtract that to the other side, so we'll get negative 233. So our shear is actually going down. Our internal shear is going down. Alright, now let's sum the forces in the x direction. Sum them to 0, and we get our newtons, or our normal, goodness, saw an n. We just have our axial forces, so those are 0. Then we'll sum our forces about the point C, which will include our moment that we already have there. So we got 600 going down, causing a negative moment half a meter away. Then our 1,733 newtons causing a positive moment, and that is 2.5 meters from that cross section. And then 900 newtons is causing a negative moment, and that is just 4 meters away. Alright, we get that our moment is equal to 432.5 Newton meters.